In this video, we will look at standard series expansion, where we approximate some standard equations using polynomials. On the right over here. As an illustration of the accuracy of the expansion, we take a look at the expansion of e to the power of x. If we approximate it using one term, you can see that we are using a horizontal line to approximate the curve, and it is not a good approximation by any means. If we include the x term, we now use a linear line to approximate the curve, which is much better than a horizontal line, but still not very good. Subsequently, the x square approximation looks like this, the x cube approximation looks like this, the x4 looks like this, and finally the x power 5 approximation looks like this. So we can see that the red curve gradually moves closer and closer to the black curve, and this means that the approximation becomes more accurate as we include more terms. In example 1, we are now asked to make use of the standard series formula to find an expression for this term of ln 1 plus 2x plus x squared. So let's recap. If I have ln of 1 plus x, the standard series expansion gives us x minus x squared over 2 plus x cubed over 3 factorial. And now, if I'm going to apply this formula for ln of 1 plus 2x plus x squared, I can group the terms 2x plus x squared together, and let's say I call them y. So this expansion basically becomes y minus y squared over 2 plus y cubed over 3, and so on. And now I can replace the y's with 2x plus x squared, which gives me 2x plus x squared minus half of 2x plus x squared squared plus 1/3 of 2x plus x squared cubed, and so on. Now I can expand and simplify. So this first term over here gives me 2x plus x squared. This second term over here becomes half 4x squared plus 4x cubed plus x power 4, which I can neglect since what I want is up to and including the x cubed term. And in this third bracket, I have 1/3. And the only term I need from here will be 2x cubed, which gives us 8x cubed, and so on. So we can combine the terms that result from here, and eventually you can show that it will be 2x minus x squared plus 2/3 x cubed. And this will be the standard series expansion of the term ln of 1 plus 2x plus x squared. In example 2, we need to make use of two standard expansions in order to find out what is the standard series expansion for e to the power of cosine x. We will need, number 1, e to the power of x, which from earlier we know is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. I stopped at the x cubed term because the question only requires me to find until the x cubed term. Next, for cosine x, we have 1 minus x squared over 2 factorial plus x power 4 over 4 factorial, which we can neglect as well. So based on these two, we can have the standard series expansion for e to the power of cosine x by first changing cosine x into 1 minus half x squared. Note that we cannot expand this straight away because 1 minus half x squared is not a small term, and we need x to be very close to 0 in order for the expansion to be very good. So let's do a small transformation. This can become e multiplied by e to the power of negative half x squared. And now we can perform our standard series expansion for this term over here because negative half x squared is small. So we will have e multiplied by 1 plus negative half x squared plus x squared over 2 factorial. But if we have x squared over 2 factorial, it becomes x power 4 since it is an x squared term that needs to be squared. So we know that the remaining terms can be neglected. And based on this, we can simplify to get e minus half e x squared. And this is the standard series expansion for e to the power of cosine x. In example 3, we are required to find out the coefficient of x power n instead of finding the expansion for the first few terms. So recalling from earlier, we have the formula for the binomial expansion to be 1 plus x to the power of n equals to 1 plus nx plus n minus 1 over 2 factorial x squared and so on until n minus 1 until n minus r plus 1 divided by r factorial times x power r. So for our expansion now, 1 over 1 plus 2x to the power of 2 is the same as 1 plus 2x to the power of negative 2. And try not to mix up the terms over here. In the formula, n should correspond to minus 2, and whereas the x power n term that the question wants us to find corresponds to the r in the formula. So let's try to expand the first few terms plus the general term. We have 1 plus n. In this case, it becomes a 2, negative 2 times x, which becomes a 2x, plus n, which is minus 2, n minus 1 minus 3 over 2 factorial times 2x squared, and so on. And finally, we have the x power n term, which is going to be minus 2 times minus 3 all the way until minus 2 minus 3 plus 1 divided by n factorial times x power n. So the term of interest is this one over here. And let's try to simplify just this term. So this equation can become simply dot 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 plus minus 2 minus 3 and so on until minus n minus 1 divided by n factorial times 2x power n. So over here it should have been a 2x power n instead of x power n. Now let's try to simplify this slightly. We see that every term in the numerator consists of a negative sign, and there are n terms in the numerator, which means if we factorize out all the minus ones, there should be n of them, which means we can write it as minus 1 to the power of n. And the terms that remain becomes 2, 3, 4, and so on until n plus 1 divided by n factorial multiplied by 2 to the power of n x to the power of n. Now we can combine the terms. Negative 1 power n and 2 power n can become negative 2 to the power of n. 2 times 3 times 4 all the way until n plus 1 is the same as n plus 1 factorial. We divide it by n factorial times x power n. And thus, this gives us negative 2 to the power of n multiplied by n plus 1 times x power n. So based on this, we can say that the coefficient of x power n is negative 2 to the power of n times n plus 1. Next, we need to write down the range of validity of the binomial expansion. And from earlier, we know that mod x must be smaller than 1. So we know that for this expansion, mod x must be smaller than 1. And in our case, we are not going to use x, but instead 2x. So I have mod of 2x less than 1. And if I solve this inequality, it becomes minus half less than x less than half. And this is the range of validity of this binomial expansion.